AP Chemistry. Today, we have special guest Madison and Marimbi joining us. We will be doing exercise 11 and exercise 15 from the acids and bases notes.
In exercise 11, we will be solving for the pH of the weak acid hypochlorous acid. A strong acid completely dissociates in solution, whereas a weak acid only dissociates slightly. Because of this, an equilibrium is established. In order to solve for pH, you must find the H+ concentration by using the acid dissociation constant, which represents the equilibrium expression. The standard formula for Ka is this for the reaction.
The hypochlorite ion OCl- is a strong oxidizing agent often found in household bleaches and disinfectants. It is also the active ingredient that forms when swimming pool water is treated with chlorine. In addition to its oxidizing abilities, the hypochlorite ion has a relatively high affinity for protons. It is a much stronger base than Cl-, for example, and forms the weakly acidic hypochlorous acid. HOCl Ka equals 3.5 times 10 to the negative 8. Calculate the pH of a 0.100 molar aqueous solution of hypochlorous acid.
In order to find the pH, we must first solve for the concentration of the H+. In order to do this, we will use the formula Marimbi showed us. Thank you, Marimbi, as well as the Rice table. The R in the Rice table stands for the reaction. To keep it simple, we will use the standard reaction. The I in the Rice table stands for the initial concentration. The problem told us that the initial concentration of the hypochlorous acid is 0.100 molar. The initial concentration for the product side will be 0. The C in the Rice table stands for the change. As the reaction proceeds to equilibrium, there will be a change in concentration X. The reactant side will lose change X, while the product side will gain change X. The E in the Rice table stands for the equilibrium expression. Equilibrium. The concentration of the HA at equilibrium will be 0.100 minus the change X. The concentration of the H+ and the A- will be the initial concentration 0 plus X, or just X. Using the equilibrium expression that Marimbi showed us earlier, thank you, Marimbi, we can solve for X and therefore the H+ concentration. Now we plug in the values. Keep in mind that during these problems we can ignore this because the value will be so small it can be negligible. Now Olivia will show us how to do the calculations.
In order to find x, we can use the solve function on the calculator. Now we will set the dissociation constant equal to the equilibrium expression. In the problem, they gave us that Ka equals 3.5 times 10 to the negative 8. We will set that equal to the expression Maddie found and solve for x. Remember that the x on the bottom is negligible.
Since Olivia found that the X value is 0.000059, we know that the H+ concentration is 0.000059. We can now solve for pH using pH equals the negative log of the H+ concentration. Plugging the X value into the H concentration, Olivia will show us what we get.
Using this value, we will solve for pH. Since the original concentration was given to us in 3 sig figs, we need to use 3 decimal places after the decimal. Thus, the answer will be 4.228.
You may be wondering, what if it's a weak base? Well, Olivia has a problem just for that.
Thanks, Maddie. Now we're going to do exercise 15. Here it is.
Calculate the pH for a 15.0 molar solution of NH3. Kv equals 1.8 times 10 to the negative fifth.
This problem is very similar to exercise 11. The only difference is that now we're solving for the pH of a weak base rather than the pH of a weak acid. We must recognize that the X now represents the concentration of the OH minus. Also, the dissociation constant is now called Kb.
For this problem, we're going to be using a specific reaction, which is ammonia plus water yields ammonium plus hydroxide. We won't be putting any values for water because it's a pure substance and it won't be in the equilibrium expression. The initial concentrations are 15.0, 0, and 0. The change in concentrations are minus x, plus x, and x, plus x. The concentrations at equilibrium are 15.0, minus x, x, and x. So, the equilibrium expression is Kb equals the concentration of ammonium multiplied by the concentration of hydroxide all over the concentration of ammonia. So let's input the values. In the problem, it said that the Kb was 1.8 times 10 to the negative fifth, and then the conc would be now here's Olive.
In order to find x, we can once again use the solve function on the calculator. Now we will set the dissociation constant equal to the equilibrium expression. In the problem, they gave us Kv equals 1.8 times 10 to the negative fifth. We set that equal to the expression Marimbi found and solve for x. Once again, remember that the x on the denominator is negligible.
Since we know that x equals 0.016432, we know that the concentration of OH minus is also 0.016432. To solve for the POH, we can use the formula POH is equal to negative log of the concentration of OH minus. Now we're going to input the x, which is the OH concentration. Now here's Olive to calculate.
Now we can use this value to solve for the POH.
Since Olivia found out that the POH is 1.78432, we can find the pH by using the formula pH plus POH equals 14.
Rearranging the equation Marimbi gave us, we can solve for pH using 14 minus POH equals pH. Because the problem originally gave us the concentration in 3 sig figs, we know that our answer has to have 3 decimal places. Thus, the answer will be 12.216.
That was fun, wasn't it? So, to recap, today we learned about the dissociation constant, which helps us solve for the pH using the equilibrium expression. I'd like to give a special thanks to our guests, Maddie and Marimbi, for helping us solve today's exercises. See you next week!